electric field E and electric potential V. Calculating the potential from the field. Now, this is electric field. We have initial point here and the particle move to F by some force. Okay, this is for force. Okay. The W equal to F dot ds integration. That's the basic mechanics. And here F equal to electric force. Okay, so this is equal to Q0E. This point has a charge Q0. This is E exerted on it. Okay, that point. Okay. And see that's one with the integration for initial point to the final point. And Q0 is constantly taken out. So this is E dot ds integration. And with them from the electric potential energy point of view, a W equal to minus Q0 delta V. Delta V is V final minus V initial. They are the same work done. We just calculate or by definition a different point of view. They must be equal. In this way, we just find compare this and this. We get V final minus V initial equal to minus integration E dot ds from I to final. This is calculating the potential from the field. Integration plus minus. This is what I try to remember. This should be independent of the past because electric force is a conservative force. Or we set Vi equal to 0. That's why we have at infinity. Okay, infinity. And then we have this infinity. This is V, the pointer. V equal to minus E dot ds from infinity to this final point position. Okay. And then this means integration plus minus. This relation, calculation the potential from the field. Integration plus minus. Sample. Figure A shows 2 points, I and final, in a uniform electric field. There's electric field going down. Okay. The points lie on the same electric field line as the point line, this one, initial point to the final point, in the same line of E. Okay. And are separated by a distance D. And this is a distance D. Okay. Okay. Find the potential difference V final minus Vi by moving a positive test charge Q0 from I to final along the path shoot, okay, which is parallel to the field. Now, by definition, V final minus V initial equal to minus integration from I to phi. Here the E is a uniform E. ds is along the direction of the E. So E dot ds equal to EDS. Right? EDS. EDS equal to EDS cosine. They are the same direction, cosine 0. Okay? Cosine 0 is 1. Okay? And E is uniform. So we take this E out. Okay? We can take this E out. And then integration distance equal to S. This total S is D. So this is equal to minus ED. Okay. Question B. Now find the potential difference V final minus V initial by moving the positive test charge Q0 from I to F along the path ICF shown in the figure. Instead, we go from here to here. It goes from here to here. Okay. We say it should be the same because the electric force is a conservative force. The work done by it should not depend on the path. Okay? Then we prove it. Okay? So V final minus equal to integration. This integration we can divide it to 2 parts. First is I to C, and then C to final. You have a final in front. Okay? Then we do it separately. Okay? In this section, E downward, S horizontal. So your angle is 90 degrees. Cosine 90 degrees is 0. This is 0. The second one, E is this direction. DS, they have angle 45 degrees. Okay, 45 degrees. So this one equal to minus cosine 45 ds from C to F. Okay. E is constant anywhere. Cosine 45 is square 2 over 2. Okay. So this one, okay, that is E square 2 over 2 is this one. Okay. Integration ds. This is length S. In this case, is this one. This one. And this one is d squared 2. D squared 2. So we get minus dE. Are the same as before. Now reverse. Calculating the field from the potential. Now we look at this. A charge Q0 is moving in an electric field. Okay. This is a two differential surface like that. This is location. This is E. Okay. Between angle at any point you have a theta, but it's angle between ds and E. Okay? And we see the dW when you move, you have the work done is minus Q0 delta V dV. The dW is what? Is equal to F dot ds. In this case, F equal to Q to E. This direction. ds direction. Okay? And this one you extend it equal to E cosine theta. The cosine theta can change. Okay? Any direction. You don't know. Okay? And so we find out, okay, we compare these two, we find that, okay, E cosine theta equal to Q0 cancel is minus dV over ds. And we round it called minus rho v rho s. Okay. And E cosine theta, what is it? Is the component of E in the direction of ds. Yeah. So this equation becomes E around direction S equal rho v rho s. This is what we get. We get a different S, we get different derivative. The component of E in any direction is the negative of the rate of change of the electric potential with distance in that direction. So Ex equal to minus rho v rho x. Ey equal to minus rho v rho y. Ez minus rho v rho z. And we have three components. We got E. E equal to Ex rho v rho x I plus Ey. Ey is minus rho v rho y j plus Ez minus rho v rho z. Okay, this is the E. Okay, we found it. Okay, and this one by mathematics is minus gradient A x y z by definition. Okay. The simple situation where the electron field E is uniform, equation becomes Es equal to delta S over delta V over delta S. We can change this one.